This is Chapter 2, VODcast 2, and we're going to start off with graphing motion at a constant velocity. We're going to look at how to interpret position time graphs. Consider this position time graph for cyclists A and B. I'd like you to take a look at the graph and try to make sense of it. On the y-axis, or vertical axis, we actually have the variable x, which you'll recall from the last VODcast stands for position. What you should be able to imagine by looking at this is imagine where the cyclists are on a number line. Here's our point 0, 0. One of the cyclists, cyclist A, starts at position 0. The other cyclist, cyclist B, starts a little bit in front. We don't know where exactly, but a little bit in front of A. So question A says, do the cyclists start at the same point? The answer to that is no. How do you know? Well, you know that cyclist B is ahead because he is higher on the vertical axis, or he is farther on the vertical axis, on the position axis. Yeah. At 7 seconds, which cyclist is ahead? Well, now we have to go to our time axis, our horizontal axis, and estimate where 7 seconds is. If we do that, if we draw a vertical line straight up and down, we can clearly see that cyclist A is ahead. A has a larger position, or farther from the origin. Which cyclist is traveling faster at 3 seconds? Now I could try to employ the same kind of technique, look at 3 seconds, but faster implies speed. And speed is actually indicated by slope. So it is the cyclist with the steeper slope that will have the faster speed. And the steeper slope would be cyclist A. Cyclist A has a steeper slope. Are their velocities equal at any time? No. Slopes are different for the entire graph. So if the slopes are different, the velocities must be different. What is happening at the intersection of lines A and B? Well, what's happening is that A is passing B. So even though A starts behind B, because A goes faster than B, and A ends up in front of B, and they pass at 5 seconds. Let's keep going. Let's look at another question. Consider the position time graph below for cyclists A and B. Question A, how does the motion of cyclist A in this graph compare to that of A in the previous graph on page 1? Well, if you toggle back and look at graph A, they really look like they have the same intercept and similar slopes. So it looks the same. They have the same initial position. They have the same average velocity. How does the motion of cyclist B in this graph compare to that of B in the previous graph on page 1? Well, once again, I'd like you to think about drawing a number line. Again, cyclist A starts at the origin and is traveling to the right. But look at cyclist B. Cyclist B starts somewhere out to the right, but is actually moving to the left. And if I were going to draw an arrow to represent its velocity, I should actually draw it a bit shorter, because B does not have as steep of a slope as A. So B starts farther from the origin. B travels left instead of right at a slower speed. Which cyclist has the greater speed? Again, we're going to look at the magnitude of the slope. Only the absolute value of the slope. A has a steeper slope than B, so A is going faster. Describe what is happening at the intersection of lines A and B. Well, here at 5 seconds, A and B either crash into each other or pass each other, and they're traveling in a straight line on a straight road, and at 5 seconds would be where they pass each other. So they pass, but they're moving in opposite directions. Which cyclist has traveled further during the first 5 seconds? How do you know? For this, we want to only look at the position axis, and we want to look at the initial position of each cyclist. So here's B, here's A, and compare that to where they end up. They end up in the same place, but when we look at this vertical axis, we can pretty clearly see that A travels a lot farther than B. So A covers a longer distance on the vertical axis. So in the same way that we looked at position, we can now look at velocity, and we can create some definitions and some symbols. So our initial velocity is just starting velocity. This is a vector, which means, again, that it has magnitude. That's a number. And it also has direction. At this point, direction would just be left or right. The symbol for velocity, or initial velocity, is v sub I. In some books, again, because it is a vector, you'll see it bolded, although I don't always write it that way because it gets kind of messy. The unit is meters per second. Final velocity would be ending speed or velocity. Actually, not speed. Ending velocity. And again, that is a vector. And our symbol would be v sub f in meters per second. Average velocity we looked at previously. That's v bar. You can define it as literally the average of the initial and final velocities, or you can define it as delta x over delta t. Both of those work. And again, our symbol for average velocity was v bar. Our unit is meters per second. Finally, we have a new one. We have acceleration. And if you have a situation like this where velocity is changing, you must have acceleration. That's a speeding up or a slowing down. Our definition of average acceleration is change in velocity over change in time. It can sometimes be written as Vf minus Vi over delta t. Final minus initial is always change. The symbol is just a lowercase a, and our units are meters per second squared. So in equation 1 here, I have the definition of acceleration written in both forms. Again, I've got Vf meaning final, or just a plain V sometimes means final. V sub I meaning initial. V sub naught also can represent initial velocity. Exercise 1 is to solve this equation for v sub f. So if I had acceleration equals v sub f minus v sub I over delta t, my first step would be to multiply both sides by delta t. And if I do that, I would get a delta t equals vf minus vi. And my next step would be to add v sub I to both sides, and I would end up with v sub f equals v sub I plus a delta t. Our exercise in question 3 then is to compare equation 2 to y equals mx plus b. So let's do that. Y equals mx plus b. Vf equals vi plus a delta t. I need to switch these two around to make it match. Vf equals a delta t plus vi. Here we go. In this situation, the slope is the acceleration, and the y-intercept is the initial velocity. The exercise next is to combine equation 2 with 1/2 vi plus vf delta t. So equation 2 is this one, vf equals vi plus a delta t. So what I'm going to do is I'm going to take vi plus a delta t, and I'm going to substitute it right in there, and then I'm going to simplify. So I'll write delta x equals 1/2 vi plus, now instead of vf, I'm going to write vi plus a delta t. And then I still have a delta t. Now I'm going to simplify. Delta x equals 1/2. Vi plus vi is 2vi. Now what I need to do is I need to distribute, and what I actually need to distribute is 1/2 delta t. So 1/2 times delta t times 2vi is vi delta t. 1/2 times a delta t times delta t is 1/2 a delta t squared. Let me just take this moment to point out that it is imperative that you have good algebra 2 skills or advanced algebra skills in order to be able to do these kinds of manipulations. Okay, we've got one more. Let's look at exercise 5. Combine equation 2 with delta x equals vi plus vf delta t, but now we're going to get rid of time. Now this is really the same two equations, but this time they're asking us to get rid of time. Now, in order to do that, the first thing I have to do is solve for time, which means I'm going to subtract vi from both sides and then divide by acceleration to solve for delta t. And then again, I'm going to make a substitution. I'm going to take vf minus vi over a, and I'm going to put it in for delta t. So let's see what happens this time. Delta x equals 1/2 vi plus vf. Now instead of delta t, I'm going to write what I circled in green. I'm going to write vf minus vi over a. Now, these are conjugates. This is actually the difference of perfect squares. Vi plus vf and then vf minus vi. We have delta x equals 1 over 2a times vf squared minus vi squared. You would actually have to FOIL this out, but I know you all remember your difference of perfect squares. Now I'm going to multiply both sides by 2a. So if I multiply both sides by 2a, I'm going to get 2a delta x equals vf squared minus vi squared. And then sometimes you'll see this equation written a little bit differently. You'll see it solved for VF. You'll see VF squared equals VI squared plus 2A delta X. We'll pause there to catch our breath, and we'll pick up on the next VODcast.